last video lecture, we have seen the introduction to fourth unit, system definition and linear system definition and nonlinear system, time invariant and time variant systems, along with the LTI systems also it will be defined, and the response of LTI system also we have seen, and impulse response is defined. So in this lecture, in this video, I am going to discuss about some more detail about the system along with the discrete systems. Okay, so the last lecture video. Similarly, in this we are going to see what is the step response. Step response of the system is nothing but the response of the system if the input is a step signal. If input is step signal, what is the use? Okay, because what is the use of giving in unit step as an input? Because unit step function is defined from t equal to 0 to infinity. So before t equal to 0, there is no unit step function. If you apply such signal to a system, it will give the runtime response. That is the long-term review, or sometimes you can long-term review, as we are always speaking about the word long-term review. If you look at the long-term review, if long-term review is better, then the system is good. Similarly, by giving unit step function as an input, it produces a long-time response. So long-time response will be given. That is the response. Also, it defines the stability criteria. Also defines by unit step response. Okay, so if input is u of t function, instead of del of t, if you apply u of t as input, the system is known as unit step response. That unit step response can be given by h of t is equal to h of t convoluting with h of t. So substituting in this equation h of tau, u of t minus tau. So u of t minus tau is defines, it is integrated with respect to tau. So tau is variable. Up to tau it will be defined. Beyond that it won't be defined. So the integrals are now ranging from minus infinity to tau h of tau. So if you solve this value, substituting u of t minus tau function, u of t minus tau equal to 0 for t minus tau is, or tau must be less than 0, or tau less than t must be less than tau. So this particular definition will be obtained. So integral minus infinity to tau h of tau by tau. Thus the input step response can be determined by integrating impulse function h of tau. If the system is said to be stable if the impulse response is absolutely integrable. The stability of system can be defined by observing the impulse response. If h of tau is less than infinity, if integral of a minus infinity to plus infinity, h of tau is less than infinity, that is, it is absolutely integrable, then the system is said to be stable. If it is not finite value, then the system is unstable. Finite value in the sense either it must be a real value, then the system is said to be stable. So response of discrete. Now I am defining the same terms which till now what I discussed in terms of discrete functions, discrete systems. So a discrete system can take discrete input and produce output in a discrete manner, that is known as discrete system. Here also the impulse response is h of n is equal to transformation of del of n. H of n is discrete system impulse response, del of n is discrete impulse function. A transformation or transformation tool is the operation of the system on the incoming signal. Okay, response of an arbitrary input. For if you take discrete system, then for continuous time signal it is convolution sum. Similarly, for discrete time system also the sum is convolution. The summation formula in the discrete manner is like this: x of n equal to sigma k equal to minus infinity to plus infinity x of k del of n minus k is the arbitrary input. Then y of n is equal to transformation of x of n. Y of n equal to transformation of x of n, and defined as like this: the transformation of x of k del of t minus k. So again transformation of del of n minus k, again it is h of n minus k. So x of n equal to sigma k equal to minus infinity to plus infinity x of k into h of n minus k. Again, it is the definition of the convolution sum in the discrete system. So output of a discrete system is convolution sum of x of n with its impulse response. So the convolution sum of two sequences is equal to y of n is equal to x of n in convoluting with h of n. So output of a discrete time system is input convoluting with impulse response. So x of sigma k equal to minus infinity to plus infinity x of k h of n minus k. Output of this is the definition of output of an LTI system. So if input is del of n, output is h of n. If x of n is input, then output y of n is equal to x of n convoluting with h of n. Properties of this convolution. What are the properties that exist in the continuous time convolution? The same properties can be exist for the discrete time convolutions also. That is cumulative property, associative property, and distributive property. That is cumulative property x of n convoluting with h of n is equal to h of n convoluting with h of n. Associate property x of n convoluting with h1 of n convoluting with h2 of n is equal to x of n convoluting with h of n convoluting with h2 of n. And distributive property x of n convoluting with h of n plus h2 of n is equal to x of n convoluting with h of n plus x of n convoluting with h2 of n. This is distributive property. Again, the discrete systems or discrete impulse function also is a response also satisfies these properties, that is cumulative, associative, and distributive. So it is very much easy if any system consisting of more than one subsystems. In such cases, you can easily find the total response of system by using these properties. Similarly, the step response is x delta v h of n convoluting with h of n, and the step response is given like this, that is h of k. Stable systems. For discrete systems also, the stable system is sigma k equal to minus infinity plus infinity h of k less than infinity. So this time domain representation. Okay. Next, transfer function of LTI, important concept, transfer function of LTI system. So the transfer function will be defined in terms of transform domain, such as frequency domain. For example, the output of an LTI system y of t is equal to the response of LTI system y of t is equal to x of t convoluting with h of t, where x of t is input, h of t is output, and h of t is impulse response. Time domain function of h is impulse response. Clear? Time domain function of a sequence, that is nth domain function of a sequence of h is impulse response of discrete function. By taking the Fourier transform on both sides, y of omega is equal to Fourier transform of x of t convoluting with h of t. So convolution time domain results multiplication in its frequency domain, that is x of t in convert h of t is equal to x of omega into h of omega. From this, you can rewrite h of omega is equal to y of omega by h of omega. This h of omega is known as transfer function. H of t is impulse response, h of omega is transfer function. Time domain response is impulse. The same impulse response in its frequency domain is known as transfer function. So transfer function is the ratio of output frequency response to the input frequency response, or output transform domain to the input transform domain. Okay, so this is known as transfer function. What a transfer function will give? Transfer function will give the spectral properties of a system. H of t will give the time domain response or time domain transient properties of a system, whereas h of omega will give harmonic or frequency spectral properties of a system. Next, system is mainly performs the filter cascade. Once if you understand that h of omega transfer function, so transfer function what I do, it is a spectral response or frequency response of a system. Once if you understand the transfer function concept, that means any system can act as a filter. it allows only some frequency components which are satisfied by that particular h of omega function, which comes under h of omega function only will transfer or applied as an output. Otherwise, remaining components are rejected. So it shows a filter characteristics. It shows that LTI system acts as a filter for some frequency components. Okay, so now we will discuss how these filter characteristics are justified in this. So that filter, there are filter is having characteristics. Spectral characteristics are having stop band and pass band. Stop bands and pass band. Ideal characteristics are different from practical characteristics. So pass band, the frequencies that are passed through the system or that are allowed by the system are known as pass band. The frequency components that are rejected by the opposes by the system is known as stop band. Filters are classified into 4 types: low pass filter, high pass filter, band pass filter and band stop filter. So low pass filter which allows only low frequency components. For low frequencies the response is 1, for high frequencies the response is 0, that is it won't allow the high frequency components, that is known as low pass filter. So mathematically they are defined as h of omega is equal to 1 for omega less than omega L or omega C, cutoff frequency. So till that cutoff frequency it allows, otherwise it won't allow. So graphical this is the output possible. Remaining all, there is no output. Remaining all are suppressed. Only these components are transferred. So this dotted line indicates the phase response. Linear phases it exhibits. Next, ideal high pass filter which allows only high frequencies. That is, for low frequencies the response is 0, but for high frequencies the response is 1. Whatever input for high frequency, that will be transfers. Okay, so this is high pass filter characteristics. So it allows the frequencies from omega c to infinity or from omega c to infinity, and remaining frequencies from 0 to omega c are blocked or stopped. So this is stop band and this is pass band. In this pass band the phase is linear. See, remember one thing, for filters are made from the RLC components. RLC components are linear components. So the phase characteristics are always linear. You don't bother about the phase characteristics. Only concentrate on the magnitude spectrum. That is, for which frequencies it passes, for which frequencies they are stopped, stop band and pass band. And ideal band pass filter, only some band of frequencies are allowed, remaining all are blocked. For example, see, from minus omega 1 to plus omega 1 to omega 2, only these frequencies are transmitted or passed, remaining all frequencies are stopped. In most of applications right now we are using band pass filter. We don't require all the frequencies. For example, if you are going to design a GPS tracker, so which is working on 2.4 gigahertz with a bandwidth of 0.025, so that band pass filter is sufficient to track a GPS or to track a WiMAX. Remaining all frequencies are we don't require. So we have to design a band pass filter which allows only 2.4 gigahertz signal only. So such designs are working right now. So that such filters are known as band pass filters and band stop filter. A part of that part, remaining all are transmitted. So a band of frequencies are stopped and remaining all are passed. So this is stop band and this is pass band, pass band, pass band. Okay, like that band stop filter will be. So in next lecture is filter designs. So in the next lecture we will see about the signal bandwidth and system bandwidth. Thank you.